Volume Calculations 2. Solids of Revolution. Consider, for example, the planar region in which y is between 0 and the square root of x, and x is between 0 and 4. A picture of this region is shown here on the right. By revolving the region about the x-axis, we obtain what we call a solid of revolution. Here's an animation that traces out the line of the resulting solid. Here's another animation in which we see the actual solid formed. Cross-sections perpendicular to the axis of rotation are circular, so a typical slice may be viewed as a thin disk. So let's suppose that a typical disk is located at x and has a thickness dx. We'll compute the volume of the solid as follows. To write the disk volume dV, we first need the disk radius. This is simply the y-coordinate on the curve, which is the square root of x. So the disk volume is pi times the radius squared dx, or pi times the square of the square root of x times dx, which is simply pi x dx. So the volume of the solid is the integral from 0 to 4 of pi x dx. This gives us pi times 1x squared, evaluated from 0 to 4, which equals pi over 2 times 4 squared minus 0 squared. So we have pi over 2 times 16, which equals 8 pi. Example. Let R be the region bounded by the y equals 2 times the square root of x, y equals 2, and x equals 0. A picture of the region R is shown there on the right. Notice that y equals 2 and y equals 2 times the square root of x intersect at the point 1, 2. We want to find the volume of the solid obtained by revolving R about the y's. So let's revolve the region and see what the solid looks like. Here, slices perpendicular to the y-axis are disks. So for a typical slice at height y, with thickness dy, we have R given by the x-coordinate on the curve. So we need to solve the equation y equals 2 times the square root of x for x. Dividing by 2 and squaring both sides gives us x equals y squared divided by 4. So the disk volume is dV equals times x squared dy, which equals pi times y to the 4th divided by 16 dy, since x equals y squared over 4. So the volume of the solid is pi over 16 times the integral from 0 to 2 of y to the 4th dy. Now this is pi over 16 times 1/5 y to the 5th, evaluated from 0 to 2, which equals pi over 16 times 1/5 times 32 minus 0. Now 32 over 16 is 2, so this ends up being 2 pi divided by 5. Example. Find the volume of the solid obtained by revolving the region bounded by the graphs of y equals x minus 1 squared and y equals the square root of x minus 1 about the y-axis. Now here's a picture of the region. Let's note here that in the x lives between 1 and 2, and y is between 0 and 1. Now let's rotate the region. This solid differs somewhat from those in the previous examples in that slices perpendicular to the axis of rotation are not disks, but rather disks with holes, which we refer to as washers. So let's consider a typical washer at height y with thickness dy. Its volume dV will be pi times the outer radius capital R squared dy minus the volume of the hole, which is pi times the inner radius little r squared dy. Notice that this can be factored and written as pi times capital R squared minus little r squared dy. Note that this is the difference of the squares of the radii, not the square of the difference. Now we need to know capital R and little r. These will be the x-coordinates on the two curves. Capital R will come from solving y equals x minus 1 squared for x. This easily gives us x equals 1 plus the square root of y. Little r solving y equals the square root of x minus 1 for x. This easily gives us x equals 1 plus y squared. Now let's prepare this for integration by expanding products and simplifying. Note that the resulting constant term will be 1 minus 1 equals 0. The first term, 1 plus the square root of y quantity squared, contributes 2 times the square root of y plus y, and the second term, minus the square of 1 plus y squared, contributes minus 2y squared minus y to the fourth, so we have dv equal to pi times 2y plus y minus 2y squared minus y to the fourth, all times dy. Now, the volume of the solid is the integral from 0 to 1 of dv. So we antidifferentiate, obtaining pi times 4/3 y to the 3/2 plus 1/2 y squared minus 2/3 y cubed minus 1/5 y to the 5th, and we evaluate from 0 to 1. The value at 1 is just pi times the sum of the coefficients here, and the value at 0 is 0. We have a common denominator of 30 here, and when we do the arithmetic, we end up with 29 over 30 times pi. One more example. Find the volume of the torus obtained by revolving the unit disk x squared plus y squared equal to 1 about the line x equals 2. Here's a picture of the region along with the axis of rotation, the line x equals 2. Now let's rotate the region to see the torus. Slightly perpendicular to the axis of rotation are the result of rotating horizontal slices of the region about the axis. Notice that again, these slices are washers with thickness dy. To write the washer volume dv, we need the inner and outer radii expressed in pi. The inner radius will be the distance from the axis to the right side of the unit circle, where x is equal to the square root of 1 minus y squared. The outer radius will be the distance from the axis to the left side of the unit circle, where x is the negative square root of 1 minus y squared. So the inner radius is 2 minus the square root of 1 minus y squared, and the outer radius is 2 minus the square root of 1 minus y squared, or 2 plus the square root of 1 minus y squared. Notice that it's important that you subtract in order to obtain the distance from the axis of rotation. So the volume of a typical washer is pi times the square of the outer radius minus the square of the inner radius, all times dy. Now we by this, so let's notice that inside the main parentheses we have an expression of the form a plus b squared minus a minus b squared, which equals a squared plus 2ab plus b squared minus the quantity a squared minus 2ab plus b squared. Notice we have a squared minus a squared and b squared minus b squared and 2ab minus 2ab, which is plus 4ab. In our situation, a is 2 and b is the square root of 1 minus y squared, so this 4ab is actually 8 times the root of 1 minus y squared. So our dv equals that times pi times dy. 8 pi times the square root of 1 minus y squared dy. Now, the volume of the torus is the integral from minus 1 to 1 of dv, which equals 8 times the integral from minus 1 to 1 of the square root of 1 minus y squared dy. This is an integral that we can evaluate geometrically. The graph of x equals the square root of 1 minus y squared is the right half of the unit circle, so the integral from minus 1 to 1 of the square minus y squared equals the area of the right half of the unit disk, which is 1/2 pi. So the volume of the torus is 8 pi times pi over 2, or 4 pi squared.